What did you eat for breakfast this
Jam
morning?
sandwich, yeah.
You had a sandwich?
Yeah.
A jam sandwich?
Yeah. Yeah, I always loved mathematics as a kid. So one of my earliest memories is when I was, I think, 2 years old, and my grandma was cleaning the windows at our home, and I was insisting that she put numbers on the she put the detergent on the windows in the form of numbers. So I always liked numbers and patterns and logic, and so things are very black and white, where there's one right answer and everything else is wrong. I didn't like sort of subjective shades of gray type questions. I would work on math workbooks for fun. You know, if my parents wanted to shut me up, you'd just give me a workbook, and I would just do sums and so forth. So I always liked math competitions. Doing that was very different from doing research mathematics. The type of problems that you're given in a problem book and so forth, these are so very canned problems, things that you can do in 5 minutes or 10 minutes. And they don't prepare you completely for a research problem where you have to spend 6 months, you have to read the literature, talk to people, try something, doesn't work, modify it, try it again. And it's a very different experience doing research, but I like it a lot better actually than all the puzzles I used to do as a kid. I don't do these things very much anymore. My mother was a high school maths teacher when she was younger, so she did help me a little bit, when I was a kid, just talking numbers with me. And then I had a lot of very good mentors. When I was like 10 or 11, there was a retired maths professor in Adelaide, which I would go visit on the weekends. We'd have tea and cookies, and he would just discuss some recreational maths problem and so forth. And it was just a lot of fun. He would tell me stories about how he used maths during World War II and so forth, to do ballistics and so forth. It was kind of fun to actually see maths actually being used for something.
He had a PhD in maths from Princeton at 20 and was appointed Professor of Mathematics at UCLA at 24.
I enjoyed it. I mean, when I was a kid, I mostly enjoyed doing maths and geeky things and so forth. And being accelerated and going to uni that early, I was around people who were older than me but had similar backgrounds. So we were at sort of the same level mathematically. So these people were 5 years older maybe, but we're both struggling with the same homework assignments. We both like to talk about various math concepts and so forth. So I felt at home. So I did miss out on maybe sort of the regular high school experience. So I didn't go to many high school social events and so forth. I did a lot of that actually once I was in grad school in Princeton. So then I hung around people my own age, and then I partied and so forth. So I sort of had a slightly reorganized childhood, but it worked out well for me.
And I have to say, Terence Tao was competing there, and he only got 1 out of 7. Let's actually cut Terence Tao some slack, the Fields medalist, the guy who's like coming close to solving the twin prime conjecture. It's actually pretty awesome because he was only 13 years old. He holds the record as the youngest person to ever have won a gold medal.
There was this question 6.
Oh yeah, that's a famous question, yes.
What's your recollection of it now, and why? And you didn't get it right.
No, I did not get it right.
How do you feel about that?
Well, you win some, you lose some. It's so long ago now, I don't remember much about it. I do remember once the Olympiad was over, I found out that some Romanian woman had solved the question, and I remember searching out her, because it was really bugging me that I didn't know how to solve the question. There was a special trick to solve it, which at the time was not a standard trick that was taught. You have to use the method of descent. You have to, I forget the exact question. You have to show that something could not be a perfect square. It was always a perfect square. And show that if it wasn't, you could find a smaller counterexample and then a smaller one and a smaller one. I think nowadays it's become part of the standard training, so they all know the trick now. But yeah.
Were you competitive? Were you the sort of boy that would get upset about it, or was it just a fascination? I just want to know I want to know the answer, or were you like angry you didn't get it?
I think I was more obsessive than competitive. Yeah, I mean, certainly I was a bit angry at myself for not getting it, but I wanted more to know the answer than to win, I think.
There's this famous image of you with Erdos.
Yes.
This photo, which
yes.
is a great photograph.
Mm-hmm.
People want to know what you're discussing in that picture. What's going on there?
Yeah, so I think he was giving me a maths problem, which I did. I think I even know what it is, because he did send me a postcard afterwards with what may be the same problem. I have it somewhere. Yeah, I think it was some maths conference in Adelaide. Yeah, I was like 10 or something. I don't remember why I was there. Maybe some maths professor at the University of Adelaide told me to come. I understand he was always very good at speaking to mathematically gifted kids. And I don't remember much about our conversation, except that I remember I really felt like I was being treated like an equal. Like he wasn't condescending or anything. Like, it was just a very pleasant conversation. I mean, now Odysseus has passed. I mean, it does have some sentimental value for me. I mean, it's yeah. I mean, I certainly wish I'd paid more attention to him. Actually, I mean, like I'd heard of him, as a child, but it's just, it was just someone, yeah. To me, he was just someone who'd like talking math to me, and that was great. He did write me a letter of recommendation for Princeton later on, so he did help my career directly.
Did you ever have people you looked up to and thought they were the top guns?
Not really. I mean, I would learn about Euler and Gauss and Newton and so forth, but these were largely just names. Yeah, I think I didn't really have a sense of, so I'd learned all these theorems and tricks and so forth, but I didn't really have a good sense of what was the most important, or what was the yeah, I didn't learn the why of mathematics until a lot later. I remember when I was learning calculus, I thought that the most important mathematician in the world must be Taylor, because Taylor's name appears everywhere in undergraduate calculus, Taylor expansion, Taylor's rule, and so forth. And he was a good mathematician, but there were many other people who did good stuff. It just is not taught as much at the undergraduate level.
When you're doing mathematics,
Mm-hmm.
do you use any kind of visualization in your head? What does it look like in your head when you're doing math?
That's a bit hard to explain. Yeah, so it's always a combination of thinking inside your head and speaking out loud and working on the board. You do try to isolate sort of the simplest metaphor or something for your problem. How can I explain it? So, for instance, I do a lot of estimates. I always want to put X is less than Y. And sometimes it helps to think of this as sort of economics problem, like you have a budget of Y, and can you afford X? That way you start thinking economically, so the way you prove inequalities, like X less than Y, is that normally you maybe try to first bound X by Z, and then Z by W, and then W by Y, and so forth. And this is like trading in one item for another item, and you get a sense of sort of what inequalities are sort of good deals for you. That you're getting your bang for your buck, and which ones are really sort of wasting your money. Sometimes utilizing sort of your financial intuition can be helpful. Algebra and topology. Those have always been my weakest areas. I've only been able to get a handle on these areas generally by translating them into other types of mathematics, geometry, or analysis. I have a better handle on. I certainly don't claim any mastery of all of mathematics, and I think nobody can do that, not since Hilbert. The work I'm proudest of is almost all joint work, and I think nowadays most of my work is joint. It is really fun to talk over a math problem at a really high level with a co-author who is really on your wavelength, understands what you're thinking. It's actually, it's saying things out loud. It somehow forces you to think like at a more organized level than in your head, where it can be a bit jumbled and vague. And it's just more fun, you can go back and forth. And if you're stuck, maybe your co-author has a suggestion. If he or she is stuck, you can make a suggestion. You're at least guaranteed one other person is interested in what you're doing. When you write a paper by yourself, there's always somehow the nagging fear at the back of your mind that maybe no one will care about this. But you at least have one person to talk about it with.
What do you think or feel, or what's your impression of those mathematicians that go the opposite way? Andrew Wiles is an obvious example. Mm-hmm. The mathematician who works in solitude. How does that impress you?
Well, what he did was very impressive. You need both. You need people who focus very, very hard on one very narrow problem and working for years, become a very deep expert. But then you need the people who can connect things from different fields. I make my living, by understanding one field X and taking some ideas from that and applying it to field Y. But I couldn't do that if there weren't people who are very deeply working in field X and so forth. So I think it's great that there's a huge diversity in mathematics. If we all thought the same way, we all had a similar philosophy, it would be a much poorer environment. So you can't really call your shots in mathematics. Some problems sometimes the tools are not there. It doesn't matter how smart or quick you are. The analogy I have is like climbing. If you want to climb a cliff that's 10 meters high, you can probably do it with the right tools and equipment. But if it's just a sheer cliff face, a mile high, and there's just no handholds whatsoever, you just forget it. And it doesn't matter how strong you are or whatever. You have to wait until there's some sort of breakthrough, like some opening occurs like halfway up the cliff, and now you have some easier sub goal. There are some speculation as to some possible ways to attack the conjecture, but nothing is really promising currently.
You're not climbing that cliff, but if a few footholds appear, you might run and try and climb it as well.
Yeah. No, this is the way it works. Yes, whenever there's an exciting breakthrough, like everyone just sort of in the area just sort of takes a look at their favorite list of open problems and say, okay, maybe this new trick can give you some advance. It's very hard to rule out that there'll be some major breakthrough, and so something which seemed impossible suddenly becomes very, very feasible. This has happened many times.
Now, we'll see that is not the same thing as the full Kakeya problem, because maybe as the direction varies smoothly, maybe the pole would have to jump around.